Good morning. We're continuing on with our CS2420 data structures class. We're looking at how we are building our linear data structures. We're looking at the last of our data structures today. We're going to look at the circular list. As you can see, we have our data structure design diagram right here where we've been working from. We've talked about our abstract base class of DoublyLinkedList, as well as the subclasses of queue, stack, and double list in previous videos. Today we're going to be looking at this one over here, our circular list. We're going to continue and look at the structure for that and go over the implementation. As you can see, we have that CircularList is inherited publicly from the DoublyLinkedList of type. And then we have, within this class, we're going to have a special helper method called findNode. We're going to be using that so we can actually have a more efficient method of getting to our stuff. We're going to, like we did in the add fast or find fast methods or get fast methods inside our double list. We're putting that into a helper method so we can automatically grab that directly from our data structure so we can have that a little bit refactored out so our code looks a little bit cleaner. Of course, we have our constructor and destructor that go along with that. We have our add and remove methods that are required so we don't have an abstract type. We want to have a concrete subclass of DoublyLinkedList, that abstract base class we've been setting up from this. We're only going to implement two specific methods as part of this. We're going to do the getFromIndex and setAtIndex methods so we can actually implement this. We could, of course, implement lots of other methods, including add front, add to end, and add index. But to just simply get the idea of how we're going to put this together, we're only going to implement these two additional methods as part of this. Of course, first we have our constructor. Again, with all of our methods and constructors, we're going to always start off with a template of class type as the prefix to our class definition methods. We have a circular list of type, owner, scope, res, and then circular list constructor. And then we call the DoublyLinkedList of types constructor right here. And again, just like in all of our other data structures, there's nothing special happening in this constructor, so we simply leave the open and close squiggles right here, and we're good to go. Our destructor will also match exactly like our other destructors. We're simply going to create a pointer reference to the front, and then using a pointer chain and a while loop, we're going to go through and remove all the pointers as we need to go down through the list. Not a lot of change for that, no big deal. We're going to look at this next is our little helper method of findNode. We've got it specified right here. It's a private method. This method would not work inside our stack or our queue, so we're not going to put it in our abstract base class because it's one that's only getting implemented in specific tools that would go along with that, including we could possibly use it inside our double list. We're going to look at this, our findNode method. As you can see right here in our documentation comments we have within this, we have specifically the idea it's a helper method we're going to be using within the class. We have a precondition right here that the index parameter is going to be within a range specifically that's going to be index itself is less than size, and index is also greater than or equal to 0. We have that as a precondition because this method is only going to be called after assert has already been called on the parameter of index, and so we don't have to necessarily call assert within this actual method itself. So it's just a way of a little saving time because this method is only a helper method, and it's already asserted that that value has been resolved, so we don't have to have that extra line in there. And again, we're returning the node that's specified by this, that index. As we take a look at the actual method itself, as you can see, this is where we create a bidirectional node of type pointer called node defined. And if that node defined that we're looking at, if the index is less than half, then I'm going to start at front and move my way up one at a time using pointer chaining up until I get to the one that's right before node defined, next pointer. Once I reach that one that is right before index, my node defined will move to that next one, and that will be at the one that is at index, resolving my node defined to the right spot. Otherwise, if I'm greater than half, or half or greater, excuse me, using that passing that I failed that if test. Then I'm going to start off at end. I'm going to check my spot at size -1. I'm going to go backwards one at a time, moving backwards through, going previous to previous to previous, up until I get to the spot where I am still greater than index. And then I'll go back one more, which gets me to index, grab me the correct pointer to the node that I'm looking for. So this is going to get me to the node I'm looking for, going either frontwards or backwards. And this gives me the time savings of about n/2. Because of the fact that I'm always only looking up to the halfway point of the list, no matter how I go, I only have to go from end to middle or from front to middle. I never have to search all the way over the entire list either way, which saves about half the time. So it's a nice little savings on what we could actually do for the data structure, given it so we can actually use this. And we'll be using this method throughout a couple different spots within the structure. Again, this is implementing the add method from the DoublyLinkedList, that abstract base class. It takes a type data parameter. Again, just like everything else, we need to create a new pointer. And we're using addme as a name for this, and it has to be a new pointer because we have to allocate new memory on the stack for this. We can actually have a persistent reference to that inside our data. As long as our size is equal to 0, we have a special case. Because when we're dealing with a DoublyLinkedList as a circular list, we have to make sure that we deal with our actual pointer references attached to this. So if our size is 0, this is the first thing we're putting inside our list. Then we want to go ahead and we're going to set this front and end both to be referencing this new pointer we just made right now. And so we now have our front end both pointed to the same exact pointer at that point. And so at that point, they're all pointing the same thing. Then we're going to take addme, the one that we just set to be both front and end, and we're going to set its previous pointer is going to point to front. So it's saying that front points to front for its previous pointer, but also that end's previous pointer also points to front because it's a circular list. It's making a circle, and we're okay. Then we also set that this selector getFront, we're going to set front's next pointer. It's going to point to end because it's pointing to itself. And again, we have just basically a node where its front pointer is pointing to itself and its end pointer is pointing to itself, and the pointer references all on that are all pointing to itself. So it's a great, lovely circular reference, and we're good to go. However, if we're adding at the end of the list, like we're designed to for most of the time, then we're just going to go ahead and grab this end, we're going to get the reference to that, and we're going to say end, oh, your next pointer, instead of pointing to it right now, pointing to the front of the list, we're going to set its next pointer is going to point to this brand new node. We're going to tell that addme node that its previous pointer is the end, okay, nice. And we're going to tell addme its next pointer is going to be front. So we're making all the connections we have to make. Once we've made those connections, we're going to tell front to set its previous pointer to point to addme. So all those lines 90 through 93, are making all the connections necessary to put the new addme node, making all the connections of both previous and front pointer for all the associated points. Finally, once we're done, we want to set end, moving it from what was the end to now point to addme, because our end pointer has to point to this new related node. And of course, we have to update our size by 1 because we have to grow our list as we add things to it. Next, we have our remove method. As you can see, our remove method is still quite big, even with our helper method being called right here in findNode. We have a large quantity of space. We're still only getting the first part of it right here. So this is one of the reasons why we wanted to create that helper method of findNode, so we can have the ability to have some cleaned up information for this. So again, remove is a required method we have to avoid abstract status. And we're going to assert, as always, inside remove, making sure the index is a valid index, make sure it's greater or equal to 0, and the index is less than this selector get size. This makes sure, of course, that we're not going too small nor too big. We fit within the range of acceptable values. We then declare a type of remove value. We don't assign anything to it yet because we want to make sure we get to the appropriate value for it. We're then to declare a pointer of type called removed. Okay, so we have a bidirectional node of type pointer called removed, and then we use that helper method findNode. So that findNode method allows us to actually just grab all that code, either going from the front and moving forward or from the back and moving backward, to get to the right node we need to actually get to and remove that node from our list. We're then to set remove value. We take this lovely temporary variable we have right here, we can grab the data out of it. It's important, again, that we make sure we get the data before we remove the node, because it's important, not only because we have the type that we're returning, but we also want to make sure we could potentially use that. Say, for example, you're taking something out of the fridge. When you remove something from the fridge, you're generally taking it out of the fridge because you intend to consume it or use it in some recipe. We're not just taking it out to throw it away. We remove things because we want to use them. And the same thing happens within our data structures. We then make two pointers. We make a bidirectional node of type pointer old previous and a bidirectional node of type pointer old next. Those are pointing to what the original removed node, in this case removed, was pointing to for its previous pointer and for its next pointer. We want to get those references. Then we have some information where we have to make some decisions. We have to check to see if our size is greater than 1. If we are greater than 1, if we have more than one thing inside our list, then we have a regular case, and we have a special case otherwise. The special case is if our size is greater than 1. So if that's the case, I'm going to set old previous, I'm going to set its next pointer to be old next. And old next, I'm going to tell it to set its previous pointer to be old previous. So I'm making sure that what was pointing to the node right here, I'm going to tell this one, instead of pointing to me, I'm going to tell it to point over here to this, and this one, instead of pointing to me, is going to point over here to this. And so they totally skip around the removed node and take it out. Now, the other special case within this, if it's greater than 1, is we have to make sure we adjust the front and or end if we need to. Because we only need to move the pointer for front or end if we're actually setting as the index either 0 or size -1. So if the index is 0, we're going to tell we're going to set the front to do this selector get front's next pointer. So we're going to move front from this spot over here to its next spot. Or if it's at end, we're going to do end and move into its previous location right here. Because that way when we remove it, we remove the associated pointer that points to it as well. And again, that way we make sure that all of our data members that are part of the thing, the state is maintained, we know where the correct end and front of our data structure are. However, if we're at the case where the size is 1, there's only one thing in the list, we can't use this set front set end capability on a null pointer. We can't tell old previous set next pointer on a null pointer, because if old previous is a null pointer, we can't do that. And so in the special case of being 1, we have this selector set front null pointer and this selector set end null pointer. We're pointing both of them to null pointer, because the original value, front and end, same thing, no longer has any way of pointing anything. So we simply just set both the front and the end to point to null pointer, thus setting it to our default case of an empty list. Once we've adjusted the pointer information, we then need to go ahead and delete the memory that's allocated for that node, adjust the slide down by 1, no big deal, like we've been doing earlier, and finally, that remove value, the stuff that we got out of the node before we deleted the memory allocated to it, we return that value so we can consume what was inside our fridge after taking it out of the fridge. And so our remove method works just the same as pretty much everything else we've done. Our getFromIndex method, now that we have that nice little helper method, look how short getFromIndex is compared to DoubleList. We look at the getFromIndex method right here, we assert making sure index is a valid size. Oh, easy peasy. We retrieve a value called retrieved. We set bidirectional node of type current is equal to findNode passing index. That findNode method, that if test that goes front to back or back to front, going to meeting in the middle, saves us a lot of code and time right here. Once we identify that current parameter, we then set retrieve to be the data that's inside that node and simply return it. Amazing. That saves us a lot of time on the getFromIndex. We really are able to do that. The same approach happens inside our setAtIndex when it's a replacement value. We're going to go ahead and return a type on this case as well. Again, we start with that same assert, making sure the index itself is valid. We declare a variable of replace so we can hold the value as we get it. We're going to again find that node that we are looking for. Again, we'll call it current because it's the one we're going to be doing. And we're going to say that replaced equals current selector get node data, and we'll tell current to replace its value with data. There, 2 lines ready to go, and finally return the replaced value right out of that. And so our circular linked list allows us to actually go through and do the stuff a lot fairly effectively. We can grow our data structure like this. And so for a circular list, we have some implementation options, including the idea of a memory pool. We can go through and have something anytime we need to go wrap around and retrieve something. We can use it to do a variety of different structures. Anytime we want to go from the end point back to the beginning, wrap all the way around. And because we used a doubly linked list, we can go either direction across that. And so it allows us to actually save some efficiencies and make things move a lot faster. Because of that, that's the reason we're using a doubly linked list and using the idea of a bidirectional node to create that project. Again, just taking a look at the very beginning right here, we went over the helper method of findNode, and that findNode is what it does is allows us to collapse our method out so our method does exactly one thing well. If we take a look over here at inherits from doubly linked list, we take a look at DoubleList again. In our DoubleList method, what we have right here in our getFromIndex, in our fast method, we have that same if test right here, if down to 129, that chunk of code, we replace it with a single assignment statement that we would put at 113 because we were saving time by having, instead of a method call, we automatically assume we want to do it the faster way. And so we have the ability to actually have that built in by using a helper method that we saw as the implementation version in our DoubleList class. We have our constructor and destructor, same basic code that we've been using the entire time, followed by our add and remove implementations, again, making sure we can put the stuff into our list. Because we're using a circular list, we have to make sure we correctly maintain where our front and end are, and then when we add to the list, that those pointers that point to both things automatically get updated. So there's a couple more pointer manipulations that have to happen compared to just a regular double list, but other than that, though, it works the same. Our getFromIndex and setAtIndex work very similar. We use that helper method again in both of those so we can actually grab that value much faster. Same thing with remove. That helper method saves time on all 3 of those methods, allowing us to do a better job and a lot faster. We'll continue on with our data structures course, looking at some nonlinear data structures, as well as a lecture on how to go over this another time. Thank you, and have a great day.